Welcome to Trout Unlimited's Cold Water Conservation Corps training video for testing water quality in local streams and rivers. The Cold Water Conservation Corps is a program created by Trout Unlimited and its Pennsylvania Council that trains a network of volunteer stream stewards to monitor water quality throughout Pennsylvania. Created to assess the impact of Marcellus shale development on streams and rivers throughout the Commonwealth. The Cold Water Conservation Corps has trained over 300 volunteers as of September 2012. By collecting data on a regular basis, TU members and other volunteers act as the local eyes and ears on the ground and become acutely aware of possible impacts of Marcellus shale development to local streams. The data collected through the Cold Water Conservation Corps is a useful tool in monitoring Marcellus shale development because it can demonstrate immediate impacts from gas drilling and capture long-term changes in stream conditions over time. This video is meant to be used as a companion to the Cold Water Conservation Corps training manual. This is the second of 3 videos in this series, which serves as an additional resource to the Cold Water Conservation Corps training program and manual. This video will show you what equipment you will need to monitor your stream, and will give you directions about how to collect air and water temperature, pH, cross-sectional area, conductivity, as well as total dissolved solids. Before you start monitoring, you should familiarize yourself with the monitoring equipment provided in your testing kit. To monitor water quality, you will need a Lamont Tracer pocket tester to measure air and water temperature, conductivity, and total dissolved solids. A tape measure, preferably scaled in tenths of a foot, to measure the width of a stream. A gauge staff, preferably scaled in tenths of a foot, for measuring stream depth. pH strips, to measure the pH of the stream water. A global positioning system, or GPS, to record monitoring locations. If you did not receive a GPS with your kit, please check with your local TU chapter and use its GPS unit. You will also need stream monitoring field data sheets. You will also need the necessary materials to calibrate the meter. If you need a refresher on how to use and calibrate the meter, please refer to Trout Unlimited's first video, How to Use the Meter. Before you begin to collect data, it's a good idea to fill out as much information as you can on your field data sheet. This includes the stream name, date, time, and general observations. The first time you visit the stream, record the GPS location, or the latitude and longitude coordinates of your monitoring site. The GPS coordinate system should be set to NAD 83, and your coordinates should be in decimal degrees. Please refer to your GPS manual for instructions on using the GPS. You will only have to take a GPS location once for each monitoring site. Now that you are on the stream, turn on your meter and set it aside. This will allow the meter to equilibrate to the temperature of the surrounding environment. This can sometimes take several minutes. Next, record the current weather conditions, any precipitation events within the last 48 hours, as well as stream flow and water conditions on your water quality data sheet. Next, using the plastic calibration beaker, wade out into the stream. Rinse the beaker several times with stream water and then fill the beaker midway with enough water to cover the colored end of the pH strip. Return to the stream bank and place a pH strip into the beaker and set the sample aside in a safe place. It may take up to 10 minutes for a pH strip to fully change color. After the temperature on the meter has stopped fluctuating and has equilibrated, record the air temperature. With the meter, wade out into the middle of the stream. Identify a section of the stream where the current is steady but not extremely fast. Look for a place where a rock in the stream creates slack water. This is a good place to measure stream conductivity. Before taking a measurement, take the cap off of the meter and make sure the meter is in conductivity mode. A microsiemens code should be displayed in the top center of the screen. This looks like US. Facing upstream, place the meter tip in the water so the electrodes are submersed. Allow the meter to equilibrate to the water temperature. Once the temperature and conductivity readings have stabilized, record your measurements on the field data sheet. Then, press and hold the Mode button for approximately 3 seconds to change to Total Dissolved Solids mode. You should see ppm, or parts per million, on the left-hand side of the screen. Place the meter back into the water, allow the reading to stabilize, and record your measurement on your field data sheet. You should collect 2 conductivity and 2 TDS measurements and average those measurements each time you conduct monitoring at a site. Conductivity and total dissolved solids can also be measured by collecting and measuring a sample of water in a container. Extreme care should be taken to ensure the container is clean and free from all contaminants before measuring water quality. To understand the fluctuations in conductivity and TDS in your measurements over time, cross-sectional area, an informal surrogate for flow, needs to be measured. In general, an inverse relationship can be found between our water quality parameters, conductivity, and TDS, and our surrogate measurement in cross-sectional area. As cross-sectional area increases, conductivity and TDS measurements will decrease. First, it is important to determine the stream's cross-sectional area, or stream width multiplied by average stream depth, at the same location each time the stream is monitored. Identify an area in the stream with moderate riffles and runs where flow is more or less uniform across the width of the stream. Remember, you will be monitoring streams during different seasons of the year, so it's important to keep in mind stream accessibility, depth during high flows, and other personal safety considerations. Once an exact location is selected, it's a good idea to mark your location with a small rock cairn to make sure you are gathering consistent and accurate data. Now we will measure the two factors that determine cross-sectional area, stream width and stream depth. Stream width will be measured using a tape measure, and stream depth will be measured using a portable stream gauge. Both measurements should be made in feet and tenths of inches. This allows for easier calculation. Stretching the tape measure across the stream, take the stream width measurement perpendicular to the flow, from water's edge to water's edge. Record the measurement in your notebook. Stream depth will be measured using the stream gauge at multiple locations across the stream. A rule of thumb is to have a minimum of 10 measurements to calculate your average stream depth. Always start your first measurement at 0, then work your way across the stream in consistent increments, recording your measurements along the way. A minimum of 8 measurements should be collected to calculate average stream depth unless site conditions dictate otherwise. It's important to note that although you start at 0 for your first measurement, you will not always end on 0 for your last measurement. Back on the stream bank, remove the pH strip from the container. Holding the non-colored end of the pH strip, match the 3 colors with the color chart on the pH container label. Color chart measurement scale is depicted in 0.5 pH units, so the colors are subject to interpretation. If you believe the colors fall between the two color schemes, determine the pH value by reading the strip at the halfway point between the two referenced pH values. After all measurements have been made, check your data sheet to make sure it's complete. A cross-sectional area calculation and averaging can be done at home or in the field. Visual observation can be done by driving or preferably walking up and down the stream and looking for any conditions that may indicate environmental damage, particularly those resulting from gas development. This includes erosion and sedimentation entering streams from construction, gas migration, fish kills, or unusual odors. A more in-depth checklist on what to look for in your visual assessment can be found in the Cold Water Conservation Corps Training Manual. Don't forget to keep records of the data you collect for each monitoring site, to provide your chapter's Marcellus coordinator with copies of the data you collect, and to upload your data to the TU Online Data Portal. This concludes the second video in Trout Unlimited's Cold Water Conservation Corps training. Thank you for participating in Trout Unlimited's Cold Water Conservation Corps monitoring program. If you have any questions about the program, contact Mitch Blake at mblake@tu.org. Thanks for your support of Trout Unlimited.